Okay, so we're going to continue looking at examples involving the kinematics equations. And this one is actually one of my favorite examples. So please pay close attention in this video because it's going to have a really cool example in it. Okay, here is our example. A motorist passes a police checkpoint moving at a constant velocity of 70 miles per hour, which works out to be 31.3 meters per second. Now, here's something that's very important. Constant velocity. That is telling you something that's very important for working this problem. What does that mean when we say that the velocity is constant? That tells us that the acceleration is zero. How do we know that the acceleration is zero? Because the acceleration is defined as the change in velocity over the change in time. If the velocity is constant, that means delta V is zero. So right away, this problem has information that we need, and we could immediately write down that the acceleration is zero. That's going to be useful for us to know for working this problem. Now, let's continue. The instant that the policeman is passed, he accelerates towards the moving car with a constant acceleration with a magnitude of a equal to 4.0 meters per second squared. Now, it doesn't actually say this, but we're going to assume that the policeman is launched from rest. And so that tells us for the policeman, the initial velocity is zero, but the a is 4.0 meters per second squared. Now, again, this a is 4, the a of the motorist is 0, the a of the policeman is 4. Both of those are constants, so we can use the kinematics equations. Now, the problem is asking, given these starting conditions, how far will the motorist get before the policeman catches up? So we've got this motorist is moving along at a constant velocity. When they pass the policeman starts speeding up, speeding up, speeding up. Eventually the policeman will catch the motorist because the motorist is not speeding up. So the question is, how far, that's going to be a distance, how far will the motorist get? So we've determined what the problem is asking for. This is like, we want to see how do we solve these types of problems. And so obviously the first thing is figure out what is the question asking for. And we figured out it's asking for some kind of a distance, how far. This basically tells us what kinds of equations we need. We know the accelerations are constant, so the kinematics equations are going to work. And we know that we're looking for a distance, so that means we're probably going to need one of the equations that has the x in it. The first equation doesn't have an x in it, so probably not going to be useful for us. At least it's not the one I would start with. The next thing that we want to do is draw a picture. I always recommend drawing a picture, and I also suggest that we set up a coordinate system to show what we define as positive and negative directions. And then it's a really good idea to analyze a problem and write down everything that you know, especially in a complicated problem like this that has lots of things given in it. And I already read through the problem to you, and I pointed out that sometimes you have to think about the problem. Sometimes it's not obvious everything that they gave you. So you have to think about it and figure out what those values are. So let us draw our picture here. We have a representation of the cop and the motorist. I've drawn my coordinate system, and I've listed what we know. And I've done for the cop is in blue and the motorist is in brown. So for the cop, we know the x0c is 0. What does that stand for, x0c? Well, x0 is the initial position, and I've got c for cop. And so the initial position of the cop is 0. The initial velocity of the cop is 0. We said he starts from rest. And the acceleration of the cop is 4 meters per second squared. Now we can do the same thing for the motorist. The acceleration of the motorist we said was 0. The initial velocity of the motorist, v naught m, is 31.3 meters per second, and the initial position of the motorist is 0. So again, the motorist starts over here, and then when he reaches the cop starts accelerating to catch him. And so he's already blowing past the cop, but the cop's going to be speeding up, going faster and faster, and they'll catch over here somewhere. So what don't we know? We don't know the final time. What does that mean, the final time? That's the time it takes for the cop to catch the motorist. We don't know the final position of either the motorist or the cop. So we've listed what we know, we listed what we don't know, and we want to find the equation that will relate what we know to what we don't know. Now, since both the cop and the motorist have constant acceleration, the kinematics equation should apply. And since we're looking for a distance, that's probably the one we should start with, the kinematics equation for position. So here I've written down the kinematics equation for the motorist. Xm is x naught m plus v naught m times t plus 1/2 a sub m t squared. So everywhere there's an m, that just means motorist. Everywhere there's a c, that just means cop. And it's the same equation down below. So this is our generic kinematics equation for position. And we know this is going to work because in both cases the acceleration is constant. And because they're different values, we need two different equations, one for the motorist, one for the cop. Now, once we have the equations that we want, we need to simplify them. And we can simplify them by simply plugging in what we know. We know that the position of the motorist was 0, the position of the cop was 0, the initial positions of the motorist and cop were 0. We know that the acceleration of the motorist was 0. We know the initial velocity of the cop was 0. And so I can plug everything, this term, for example, since that a is 0, that makes this whole term 0, because anything multiplied by 0 is 0. All these terms with the little red arrows, they get eliminated. And so I can simplify. I've got two equations, an equation for the motorist, which is the constant velocity of the motorist times the time, and then I've got the acceleration for the cop, which is 1/2 the acceleration of the cop, t squared. So what is that equation xm? That is the position of the motorist at any time t. What is xc? That's the position of the cop at any time t. I plug in 3 seconds here. That'll tell me how far the motorist has gone in those 3 seconds. I plug in 3 seconds there. It'll tell me how far the cop has gone in those 3 seconds. Okay, so the next thing we want to do is sometimes, it's not just enough to plug and chug. We have to think, what do we know about these problems? How can we find paths to solve these puzzles? You have to think of these like puzzles. And so there's one key fact that you have to recognize in order to work this problem. And it's the idea that the cop catches the motorist. What does that mean? Because we want to find how far when the cop catches the motorist. Well, that means that they have the same position, that the position of the cop equals the position of the motorist. Once you recognize that, we can set those two positions equal to one another. And so we had an equation for xc, we had an equation for xm on the previous page. So we'll just equate those two equations, and then we should be able to solve for what we're looking for. So let's do that. I've got my position for my cop is equal to the position for my motorist, and I plug in, I get 1/2 a sub c, that's the acceleration of the cop times time squared, equals the velocity of the motorist times time, that's the x of the motorist, and I can plug in my values here. Now, I told you that that would solve what we're looking for. Actually, I lied a little bit. That won't give us what we're looking for, but it will give us t. We have an equation where the only thing unknown is time. And what time is this? If I solve this equation for t, that will give me the time that makes this equation up here true, that the cop and the motorist have the same position. So I'm going to solve this for time, and then I can plug that time into either there or there, and that will give me the position. They're the same position, so I can pick either one. I'd probably pick that one because it's easier, but either one should work. So our equation has the form, we had 1/2 4, that leaves us with 2. And so we've got 2t squared minus 31.3t. Now, when you guys are actually doing these quadratic equations, especially when you have to use the quadratic formula, the units get really messy. And so this is the one time when I'm willing to let you just drop the units. So we'll just plug in the numbers, but we're solving for t here. Now, we want to solve for t. We could actually use the quadratic formula and apply it to this equation, but because there's no constant term, it's actually probably easier just to factor out a t. And so I've done that here. I've factored out a t. If I multiply this t through this parentheses, I end up back with what I have up here. But t times the stuff in the parentheses is now equal to 0. That means I'm set up to get both the roots of this quadratic equation. T equals to 0 will solve it, or the stuff in the brackets will solve it. And so either t equals to 0 or 2 meters per second squared, that's the acceleration times time, minus 31 meters per second, that is going to be equal to 0. And if I set the stuff in brackets equal to 0, I get that the time is 15.6 seconds, and that is the time when the cop and the motorist have the same position. And so also t equals to 0 is the time when the cop and the motorist have the same position. There were 2 times when they are at the same position, and these are those 2 times, when it started and when they get caught. Now I can take that time and plug it into either of the position equations and find the distance. And so if I plug it in the equation for the motorist, I get 488 meters. If I plug it into the equation for the cop, I get 487 meters. That's 1 digit off, but within sig figs, that is the same answer, which is what we expect. And so that is how far the motorist makes it before the cop catches them. And that is the answer to the problem.